In the previous video, we have seen how you can write VHDL code for your logic and then how you can simulate it in Xilinx ISC suite, right? So I recently came to know that Xilinx ISC suite is actually outdated, and the last update is on 2014. So it is really outdated, right? So we are going to use Xilinx Vivado from now on for both the HDL and Verilog coding. So you can simply go to Google and simply search for it, and you can actually see this icon. This is Vivado. This is how it looks, and the website symbol is same thing. It will look something like this. So Vivado is developed by Xilinx as well. So you can simply search for Vivado downloads. Mm, So you open Vivado, and this is the website where you can download Vivado. And simply click on this, and it will open this thing, right? You can simply scroll down, and then you can download this. After downloading this, you can simply run the setup, and it will ask for a lot of options, and you can install it. I will make another video if possible on how you can install Vivado. And after installing Vivado, it will take a lot of time to install Vivado because it will download a lot of stuff from internet, because there are a lot of devices and netlist files it required to simulate for simulations and RTL synthesis and stuff. So it will take a lot of time to install, but you don't need to worry about it. You can simply put it in the background and you can do your work. So after installing, you can see these icons, but don't get confused with these two icons. So this is the Bytes model composer. We don't use this in our VHDL tutorials, but we will use Vivado. So this is the Vivado icon, which is Vivado 2024.1, right? Now I'm gonna open this. It will take some time to open the Xilinx Vivado. So now after you open the Xilinx Vivado, it will look something like this. So you can simply click on create project, and then it will open a wizard to create a project, right? So you can simply click on next, and then you can give a project name, which gets, and you can select a folder name here. So I'm gonna select this, and if you click on create project subdirectory, it will create a subdirectory. But if you already created a directory, then you can simply uncheck this. And then next, and then we are going to do RTL project, which is, so you can do everything, right? So you can synthesize, you can implement, and then you can create block diagrams and everything. So I'm going to go for this RTL project, and then I will click on next. And after clicking next, it will ask for you to add sources. So sources are nothing but our VHDL source files and test bench files. So for test bench, we will add it in the simulation part. So we will put the test bench aside for a minute, and we will create a source for a VHDL source or logic source. Right now, I'm gonna click on create file, and then I will give a file name of basic case, and then okay, next. And we are not going to add any constraints for our project, so I'm going to click next. And these are the ICs. We can simply see there are a lot of ICs, right? You can click on anything, and if you are doing your logic for a particular IC or a board, you can select that. You can also select boards here. You can get them from internet as well. This you always use it. If you click on refresh, it will get all the boards from internet. So these are the installed ones. You can click on these one as well. Zinc. Most of the time, many people use Zinc, right? So you can also click on Zinc. So, but I'm gonna go with the default one, default selected one. So you can also select anything you need, and then just click on next, and it will show you what you selected and what you described in this project. And then you can simply click on finish. It will start initializing the project. It will take around 2 to 3 minutes to initialize the project. If your PC is faster like mine, it will be even more faster. So now it will ask for port names. So what these port names are simply, it's nothing but inputs and outputs, right? So we will have two inputs in basic case, A and B. In this project, we are going to use only two inputs. So A and B, and then we have Y end, Y or, and Y not. These three will be the outputs, and then I'll click on OK, and it will update your code. If you are wondering, it will show the state of this software in here, files, state of the files, right? In here, updating or something else, and then it will show the software state in here. So it shows ready. So everything is ready. So I will if I have to double click on this. So after I double click, it opens your code in this window. So we can simply it will generate the source code, right? Source file for only source file. We have to write code on our test bench. So what we have to do is the same thing as we did in the ISC suite. So if you didn't watch the ISC suite video yet, go and watch it because I explained a lot of things in the ISC suite video. So and I will explain a little bit in here as well, and so you don't need to worry about it actually. But it's better to watch that video as well because you'll get a simple idea on how you can write VHDL code and what these keywords does. So we already know that inside begin function is where we actually write our code. So uh, inside begin, we will assign yn to a and b and then six semicolon. We all know that. And then y or a or b, and then y not a. So you can actually see that it's showing my suggestions whenever I click on we click on a letter. Like for example, if I click on A, it will show me the suggestion. So these are the keywords I can use that starts with A. The same way we can click on any letter, it will show you suggestions. But in ISC suite, there is no such facility for writing our code. But in Vivado, there is this feature which is known as code suggestions. You can actually see these features in IDEs and code editors. So in Vivado, it will show that. So after I click, after I saved it, you can see that updating it did, right? So now our source file is completed for basic gates. Now what I'm going to do is I'm going to click on this, which is add sources. Now we are going to create the test bench file. So it is a test bench file is basically a simulation source, but not a design source. The source we just wrote, the logic we just wrote in the in a file called basicgates.vhe, right? This is the source code. We can also say it as a logic file, source file. Now we have to create a test bench file for this source file. So I'm going to click on this, and it is a simulation source. I'm going to click on add or create simulation sources, and then I'll click on next. Now we have to create a simulation file. I mean, a test bench file. You can change the folder name here, or it also it by default it's sim_1, right? So you can, if you want to create the new set, you can create a new set, but I'm going to go for default, and then I will click on create file. You have to choose VHDL because we are doing VHDL, right? If you are doing in a Verilog, you can click on Verilog, but we are doing VHDL, so I'm going to use VHDL, and then basic test bench. So there is no rule that the file name, the test bench file name should match with the source file name. You can give any name as possible. But personally, I like organization, so I use base gates and test bench. So after giving the file name, I'll click OK, and you have to click. It will be checked by default, and you can simply click on finish. Now, after you click on finish, it will ask for the port names again, like it did for our source file, right? Source file for VHD. So we will give A and B. You can give any port numbers, but when we are matching the ports to in the unit test, we have to map the ports exactly. Like for example, if I give A instead of AB, if I give A TB and then B TB, test means, right? So if I give this, we have to put the A TB to A, like A TB after. It's better if I show you. So why I will give TB for all the ports in test bench. Y40, why not? It's fine. Now I will change this to out and then I'll click on OK. And now we can see that it's updating. And then after it stops updating, we will have a simulation source inside simulation source folder. So I will open this and I will open this again. And this is the file we just created, basic gets test bench. I can double click on it to open it and it opened it. So now inside this, unlike in Xilinx ISC suite, we can see that it is same as the basic gets.vhd, right? Both are almost same. So there is no, it is not actually test bench yet. So what we have to do is we have to modify some things inside this basic gets test bench file. So first things first, we have to remove these port ATB and stuff. So I'm gonna control all this, and then you can go here and then you can initialize the component here. So component. So the component, and then it's followed by the our source file name, which is entity name, which is basic gates, right? In basic gates VHD, we have an entity name called basic gates, which will do all the operations of basic gates. So which is y and y or and y not. So and or and not operations. And what will do y and or and not operations is basic gates. And we defined basic gates as the entity, and we are going to use this entity inside a test bench. So component, and what is the component name? Basic gates. And now we have to define the port names, which are is port A, which is an input and follows the STD logic, and B, in which is STD logic. We can write same things as we wrote in that file, right? And y and is an output which follows the STD logic again. Y or, which is an output and follows STD logic underscore STD underscore logic. And y not is also an output and also follows STD logic. Now we have everything. We have initialized the component, and now we have to end the component. So end component. So now we have created the component, and then we have ended the component. We can use this component later on. Now we have, what we have to do is we have to initialize the signals. So what the signals are, I have explained in the previous video. You can go and watch it, but I'm gonna write the statement. So in a simple words, you can define signal as a in simple words, you can say them as the mediators or something like that, or you can also say them as a temporary variables, right? So if I write signal A, and what is A? It is an input, and it follows the STD logic, and I'm going to initialize this A, which is this one, right? In component array, I will initialize this with 0. So these are like the default values. Signal A, and signal has the default value of 0, and then signal B, STD logic, which will be 0 as well. These are the input signals, which are A and B, and I'm giving a default value of 0 and 0 inside A and B. And now I will do and write yn, which follows STD logic. But this y and or and not depends on A and B. So we cannot really give a default value for this, and because they are dependent, right? So same thing with other variables as well, or STD logic. You can see that the suggestions are actually showing faster now. STD logic. Now we have initialized the signals as well. All we have to do is we have to create a unit test now. So let's create the unit test. You can create unit test inside this UUT. UUT is saying this software to initialize the unit test. And then we have to give the entity name, which is basic gates. So basic gates. And then we have to we have to map the ports now because we have signals, right? A, B, Y, and YR and Y not. These are the signals we have. Now we can simply port them with this. So previously we have created the ports in a task, right? We are not going to use them. So, but it is a mandatory, process. During the process, if you don't initialize the ports, it won't create the file. So even if we give the port names, we are simply commenting them. So there is no use, there is no real use for that. So if you these are the things that you have to keep in mind because these are like the variables we have in general programming languages. There are these variables, right? So these are similar to variables. Now we have to port the maps to this unit test. So what I'm going to do is I will simply click on port map, and then I will port A to A. So we have A right here. We have entity A and B, which are inputs, and Y and YR and Y naught are the output. So we can simply do this B and B and C. There is no C. Y end, Y end, and then we have YR, YR. So is it the last one? Y naught. There is a still Y naught, Y naught. And now what we have to do is we have completed the port map. So we will begin a process. After initializing our unit test, we have to start our process, which will we can simply write process and then end process, because if we forgot to write the end process, it will show me an error. So I'm gonna simply create end process, and then inside this process, we have to write begin, and now we have to write the process inside this process block. What this basically does is we are just saying that whatever block we write here is a process, a simulation process. So we will just say that from here onwards the process will start, and then we will begin the process. And inside process, what we have to do is we have to write our truth tables and stuff. For example, we have two variables in our this project. Specifically, we have two variables, which is A and B. So we will have a combination of four combinations. So the first combination will be 0, 0 and 0, 1, 1, 0 and 1, 1. So what we have to do is we will initialize A with 0, 0. We will give A, B as 0, 0 and wait for some time. We will give A, B as 0, 1 and wait for some time, and so on. So we can simply do that by just doing A, and then we will just do this A and then B, and then we can simply write it this way, equal to 0 and then B 1, 0, 1 condition, and then this will be 1, 0 condition, and then finally equal to 1 and then B equal to 1. So if you write just like this, there will be a problem, because if you write like this and if you run the simulation, what happens is the board you selected at the beginning of the project might have some frequency, some clock frequency. So everything in an IC depends on clock frequency. If the high frequency is very high, the time will be little, very little. So the delays will be very little, which will in turn increase this speed of your IC, right? So what happens is when you write simply like this, it will set 0, 0, A to 0 and B to 0. It will produce as the output, and it will just it won't wait for until it won't wait for any time. So so if you run this program as it is in the output waveforms, you would only see some either one or zero, because there is no time for us for to look at this, right? So it's not waiting. There is no delay. So if we implement delay, we can just see these outputs very clearly. It will perform all the AND, OR, and NOT operations, but it will be very fast. So we cannot observe them in the output waveforms already. So what I'm going to do is I will add a statement called as wait for, and then we will give you the delay of 100 nanoseconds. You can give as much delay as you want. You can also give as 1 second delay, but 100 nanoseconds is enough for our observation. So I will add this for every case. Wait for 100 nanoseconds. So we don't need to put this for the final statement, because this final statement will just be a final statement. So we can just simply leave it that way. And this is the end of the test bench. We can simply do this, and if we save this, it will start updating and it will show if there are any errors or anything. You can see that whenever after some time it actually there is only one sources here, right? Before there are two things, which is basic gates and basic gates tb. Now we can only see that basic gates tb, and if you maximize this, you can actually see our source file, which is basic gates.vhd. So what basically happens is when you write this statement, especially when you write this statement, uh, it will create a test bench. So this is what the test is. So the test bench uses a basic gates file. So that is why it is inside the test bench. So inside test bench it is using that. So that is why it just shifted the um, basic gates file into test bench. But in your if you see this in the folders, it will be different folders, so you don't need to worry about it. So we have saved both our source file as well as test bench file. Now what we have to do is the same thing we did in the ISC suite. Now, but the thing is, in ISC suite, we actually clicked on check syntax before we ran it, right? We clicked on both check syntax and then behavioral check syntax. But inside this, you don't need to do both the steps. They are automatic. So when you have an error, it will show you an error directly after you save the file. So you can just keep those two steps inside Vivado. So after that, what we did in the ISC suite is we run a simulation. So we can click on run simulation and then run behavioral simulation. If you watch that video, if you watch ISC suite video, then you will understand what we did in there and what is the difference in here. So if you can run behavioral syntax and simulation, and it will run the simulation. It takes a little bit of time to run the simulation and other processes. You can see that we have simulation here, and then linter, and then we have synthesis, and we have implementation as well. There is another called actually 10-bit stream. I will talk about it in this video. So after I click the run behavioral simulation, we can see that it's almost as same as Xilinx ISC suite, right? Now everything will be same. You simply go on here and click on this. There will be a same this icon like this, but inside there will be no minus or plus, but there will be this icon inside the ISC suite for ISC suite. But in here, we just click on this and it will show you these waveforms. So this is the final output. So what happened is we didn't give 100 nanoseconds delay at the beginning of that, right? So that is why let me go for the basic edge test bench. You can see that we didn't give any delay at the beginning, and that is why you can actually see in the waveforms A has a delay of 200 nanoseconds, but B has only 100 nanoseconds, right? So we will give a delay. First of all, whenever you run a simulation, you have to close the simulation before you read the code, right? I will close the simulation. Uh, okay, and then it will close the simulation. And now I will give a delay of 100 nanoseconds before initializing a and 0 with 0 and 0. Now I will save this. Same thing, it will update the code and it will check for syntax errors and warnings in here. If there are no, if there are syntax errors, it will show you that it will show you a red squiggly underline, right? Or you can also go for the messages and you can see all the errors and warnings and stuff you can see here. So now what I'm going to do is I already saved it and then I will click on run behavior simulation again and it will start the simulation. It will execute the simulation and you can now see that if I click on this, now you can see that they actually change, right? Mm. The waveforms looks the same as in ISC suite and you can just drag these, whatever you call this, the different parts of the waveform and you can see the corresponding values and you can check it. Right? So now what we have to do is we got the simulation results and then now to create the block diagram for this logic, we can simply click on run linter. And when you click on run linter, it will generate a block diagram like what gates you are using, what gates you are going to use in this logic, right? So okay, when you click on run linter, it already ran, and now you can open this open elaborated design, and you can simply click on schematic, and it will open the schematic in here. It will take some time if your PC is a little bit slow. It will take some time to load these files, right? But it will eventually open it, so you don't need to worry about it. Or you can simply click on background here. It is also showing you an option background. If you click on background, you can do other operations in this. So it's loading the balance. There we go. So we are using y naught, y end, and y r, right? So this is the circuit diagram Vivado generated. And for the block diagram, you can create either block diagram here or you can simply click on run synthesis. And then I'm gonna put the default locations and then okay. And it will generate it will synthesize your design, right? You can see the synthesizing, there is a synthesizing and implementation here. If you click on create block diagram, it will actually create a block diagram and show them. Click on this. Then if I click on OK, it will create a block diagram. It will take some time to do both of these synthesis, implementation and block diagram. It will take some time, but it won't be very long. It will be long, but not very long. So it didn't generate anything yet. It's fine. We don't really do the create block diagram in IP integrator, right? So we will just close this. And if you go for design runs, the synth is still running, synthesizing, right? It is synthesizing. So you can actually see that here as well, running synth design. Now you can see that there is a tick mark. When you see a tick mark, that means that the synthesis is over. So you can click on if you want to run the same implementation. So what this implementation is, the implementation of your logic and in the device you selected, it will show you the block diagram. It's like in the textbooks we have the architecture diagrams and stuff, right? It will show you that kind of diagram. I will show you after this. So you can click on OK, or you can click on cancel and then you can click on run implementation, but I will do the implementation right now, so I'm going to click on OK and then you can click on OK again. Now it will start the implementing, so you can see that here as well as here. So it takes some time to implement the design and logic we just tried, we just wrote and then generated, well. So it will take some time. You just have to wait until the process is done, because or you can simply do other works if you have, but it will take time for synthesis and implementation. If your PC is fast enough, it will be even more faster. So let's wait for until the implementation is done. Before that, we didn't see the synthesis result, right? So we can just go here and then we can go all the way down here, and then if you click on schematic, we'll open the schematic in this window. These are the this is how it will implement in your board or IC, whatever you choose at the beginning of this creation of the project, right? When you created this project, you ask for either a chip IC or the board, Zinc boards, or we selected XP something, right? The default one. So that this is the implementation in your board. And if you see the architecture, it's actually running the architecture right now. So after this is completed, we can actually see how it implements inside the IC. So implementation is done now, and we can click on open implemented, or you can simply click cancel. You can, if you click on open, it will open here in this window again. So this is the implementation in your IC or the device you chose. So I'm gonna minimize all these things, and then if you click on zoom in, you can actually see these things, right? So it uses this thing and this part and this part. So this is the implementation of inside the device you selected. So this is how you create the VHDL files, and then run the code and create block diagrams and verify it in your device. So if you want to do this directly in a board, you can connect your board to your PC, and then you can click on generate bit tree. I cannot do it because I don't have the board I selected right now. So that's it for this video. Thank you.